Okay, so today's lecture is about Boolean functions, Boolean analysis. It's really going to be, well, it's going to connect to what we did last time. It is going to have some technical connection, but I think, given the time constraints and the semester and stuff, won't really be able to do everything in full detail. So this is also partly just sort of a survey or an introduction to the area, and at least I'm not prepared to do the whole chapter that's in the notes. And then I'm going to ask you guys at the end whether you would prefer a part two to this and finish off that chapter and make all the connections, or just to do something completely different next week. Either one's fine. Uh, Otherwise, I would just choose whatever might be fun or seem fun. I'm out of notes. We've done like 350 pages. So, even if I do something interesting next week, I don't know if I would have like nice, clean lecture notes in time for the final and stuff anyway. So it's not going to be a major point of emphasis on the final, maybe a multiple choice or something, right? So I'm not trying to increase a lot of material next week, maybe just do something fun otherwise. But anyway, I'll ask you guys at the end if you found this part of it interesting or you're completely over it, which is completely fine. I think I think last time I taught this, the class was completely over it by the end, so I hope to do a little bit better this time. But it'll at least give you enough to read the rest of the chapter if you're interested and kind of see really the missing details that we omitted last time from the PCP theorem, which is quite the result. So maybe not now if you're feeling busy, but maybe someday you would like to understand how all that works, in which case you should be mildly prepared by the end of this lecture, and I think that's pretty good. Okay. All right. Okay, so let's get started. Um, all this stuff we've been doing all semester, it's unbelievable. You guys probably know better than me. Okay, so last few classes, we were doing this dramatic PCP theorem, and this was based on probabilistically checkable proofs and the idea that you don't actually have to look at the whole proof exactly um, to conclude with some confidence whether or not your input X is part of the language under consideration. And besides being a profound statement about computability and proofs and stuff like that, it also leads to very nice things like hardness of approximation. And okay, so the approach we took, there's other proofs, but the proof that we studied was based on studying this graph CSP problem, constraint satisfaction problem, but only two variables per clause, in which case you can kind of think of variables as vertices and clauses as edges. And kind of the overall structure of the proof is that, we know that, say, getting 1/mth kind of approximation, knowing whether or not it's completely satisfiable or if 1/m fraction is unsatisfiable, that's already NP hard because 1/m was the minimum non-zero value. And the goal was to gradually transform that graph CSP into somehow more layered or redundant CSPs, so that minimum unsat value kind of goes up and up and up. And eventually we're able to show that you can get up to at least some constant. We didn't really go all the way to 1/2. That would require more care, but otherwise same kind of high level ideas. But still you get some constant gap and show, okay, it's actually NP hard to decide between whether it's completely satisfiable or if there's some constant that up to which it can or cannot be satisfied, which is quite strong. The style of the proof is sort of brings a lot of different ideas together. But the reason we like graph CSP is because we've developed all these tools to sort of play around with graphs and do interesting stuff with graphs. So actually, insofar as we understand random walks on graphs, we're somehow able to get these very strong complexity results, right? So most of our discussion was analyzing this powering thing and things to do with the spectral gap. But the third step, which I rushed a little bit for lack of time, was this alphabet reduction step. So let's see. Right, so if you remember, the powering roughly is taking a graph and powering the graph and then making appropriate changes on the CSP side. But one cost of it is that the size of your alphabet went up. kind of exponentially. And you want to keep that as roughly a constant. So when to a constant to e to that constant or something, but we want to bring it back to a much smaller constant because if you kept doing that, that would be a problem. And that's where this alphabet reduction step comes in, okay, which was a two-step process. The first step used error correcting codes. That's, I think, kind of a surprising connection. And what it kind of does is it blows up each vertex into like a bit string, where each bit becomes one vertex. But now your CSP, instead of having two variables, sort of has those two bit strings worth of variables. So it's no longer a graph CSP. So what you kind of have is sort of like this big hyperedges or some kind of boolean function. And you kind of want to come up with like an equivalent graph CSP. You want to replace it with a graph, but roughly embed the logic still. Okay. So step one was this error correcting code thing. That was kind of interesting. But step two, we just applied sort of as a black box, which was sort of, oh, for each of these Boolean functions, I should be able to kind of replace this black box function. It's still constant size, so you can poke around and learn everything about it in constant time. And try to somehow replace it with some kind of graph CSP that roughly reflects the logic of that Boolean function. Okay, and we just assumed this as a black box and saw how it all came together and just wrapped up the PCP theorem at the end of last class. So the goal of this class is to shed some light on this part of it and also expose you guys to a little bit of the math and what's going on. So, okay, so that that black box we need is going to be strongly related to the third algorithm here. So we'll do something called property testing. Okay, so part of the goal of this class is just expose you to, oh, what is property testing, give you one or two examples. Lots of people work on property testing. The universal tester is the thing that translates to what we need for the PCP theorem. Okay, and to analyze these things, we have to do something involving the fancy word Fourier. Although it's, I mean, for us, it's just going to be some mathematical thing, and it only takes one line or something. But somehow, it's really just a change of basis to a different basis. But it lets you sort of see things in a different way, and somehow clever things come out. And hopefully, the one or two proofs we do together will, I don't know, at least surprise you and be interesting. So I don't know. I don't think we'll actually be able to get to these two very much, but I will talk a little about how to use this thing for PCP. I think we'll be able to cover linearity in full, and at least be able to explain the dictatorship test. And that roughly takes us to like 2/3 of what's written in the notes. Okay. Okay, any questions? Okay, so in this general line of work, we're analyzing Boolean functions as a black box. Okay, so f just takes some bit string and outputs some real value. Okay, and the only way we can access f is just by querying it. Oh, what's f of this? What's f of that? Okay, so you just play 20 questions and see if you could say something interesting about f. Maybe is f a linear function, for example. Okay, and okay, so the obvious appeal is that arguably like any algorithm is a Boolean function, right? It takes at least if you think of like Turing models, they're supposed to like take in as a bit string and they output yes or no, right? They accept or reject. So there's something very universal about this model. It's like, oh, if we can analyze this, we can analyze anything. That's great. For the same exact reason, it's like, oh, we're screwed. Like this captures everything. We probably can't say much, right? But so I think what's kind of surprising is that you could do some stuff. You could do some useful stuff. We could do enough stuff to give the last step of that PCP theorem. That's certainly good enough for me. Okay. Although, of course, we won't be able to do much exactly without querying everything exactly, but we don't want to do that. There's 2 to the n inputs, and that's sort of silly. Okay. So we'll be doing things randomly, approximately, and seeing what we can get. Okay. All right. So, yes. Okay. So property testing. So, yeah. So given f, You want to test if f has certain properties. So testing, I guess, just the word test probably emphasizes two things. One is probably going to be random, and two, that we're not trying to query everything. We're just trying to poke a few holes and see if we can learn something about it. Okay, so okay, so the one famous one is just linearity, trying to figure out if a function f is linear or maybe linear mod 2. Okay, the word dictatorship is roughly saying, is f just a function of a single bit? Okay, so is f of the form like f of x is equal to -1 to the xi for just one bit xi? So if that bit is 0, that'll be 0. If that bit is 1, or no, if that bit is 1, it'll be 1. Okay, it doesn't matter. Okay, so okay, right. And yeah, we're trying to limit the number of queries we make and see if we can do something more clever than querying everything and double checking everything virtually, which of course is not very interesting. Uh, but of course, as soon as you do anything less than checking everything, it's going to be hard to be exact, right? You're never going to know about the one thing you omitted, except for maybe some funny symmetric situations. But for the most part, you won't know what's going on with the one or two things you haven't queried. So you won't be able to do things exactly. But if we allow for randomization approximation, maybe we could do some interesting stuff. Okay. All right. So here's the main result that motivates this lecture. When I wrote today's main result in the top right, I really thought we were going to be able to cover it. And slowly over the course of the day, I realized, oh, we're not going to get there. But it's still important, I think, to introduce, and we'll start talk about how to apply it to the PCP theorem. Okay, so let L be some fixed language. So you're worried about whether or not X is in L, X is not in L. And let P be equal to 2 to the 2 to the N, something much bigger than N. Okay. All right, so it says that there's some randomized algorithm, a testing algorithm. It takes as input an n-bit string and a p-bit string. Okay, we're going to think of the p-bit string as like a proof for X. So that if you're given access to X, which is your n-bit string, and Y, which is your p-bit proof string, okay, it'll only query 3 bits of X or Y. Okay, it's only going to look at 3 bits. And if X is in the language, it'll always answer yes. If X is not in the language, then for any proof string, it's going to say no with some odds proportional to the distance from X to the nearest point Y that's actually in the language. Okay, so let me parse this bottom part. So this is the L0 norm, so it's the Hamming distance, how many bits are the same or how many bits are different between X and Y. It's taking the minimum over all the Y that are actually in the language, and then dividing by N just makes it like, out of N bits. Okay, so it just makes it a fraction. So the odds of rejecting should be, say, 1 over 1,000 times times the relative Hamming distance to any point that's actually in the language. Yeah. Yeah, that Y refers to the proof. Okay, yeah, so if X is not in the language, then for any Y you give me, oh, bummer. Okay, I see what you're saying. All right. We have 26 letters, but it is convention to minimize the number you do, and that just gets us in trouble. Okay. All right, is that better? Yeah. All right. Okay, so yeah, the minimum distance from any other point that's in the language. Okay. All right, so this looks a little bit like the PCP theorem, but there's a couple differences. And they're lined up on the next slide. Maybe I can ask you guys what sticks out. Uh, what's one difference between this and some of the stuff from the PCP theorem? Yeah.
In the PCP, if I remember correctly, the proof has to be polynomial in the length of the input, right?
Yeah, so first P is allowed to be much bigger. One reason that's going to be okay for us later in that mini step of the PCP theorem is that we're only going to apply this to those individual clauses which have constant size. So we're just blowing up a constant, so we kind of get away with it. But if n is otherwise a real variable, then yeah, this is quite long and sort of inefficient. It's not trying to be efficient. Maybe one more. I don't know if this is a little hard if I didn't put up the definition of PCP. Okay, so that's 1 out of 2. Um, the other one is that the PCP said, oh, just reject this probability at least 1/2, like a fixed constant. And here we have some error that's proportional to the Hamming distance from L, which played some role in the proof last class. I think those are the two main differences, but it is similar in spirit, maybe weaker in some ways. Okay. All right. So let me at least explain the algorithm. I mean, this looks like such a complicated claim that you might think the algorithm is very complicated too, but in some ways it's not necessarily. In fact, all of these testing algorithms tend to be very simple, and it's a little bit messier to analyze. Like the ratio of analysis to code is like very high, I feel like, in this section of the notes. Whereas like last class, we spent most of the time even describing what the construction is, and then the analysis was actually quicker. Okay. All right. So, okay, sort of a funky thing. All right, let's let capital N be 2 to the n. Okay. I'm going to let chi I think chi is x, right? So chi I is defined as -1 to the xi. So that's 1 if xi is equal to 0, -1 if xi is equal to 1. Okay, so it's a dictator function is the name for it. Okay. Now, let the dictators of L be, okay, so L is a subset of all bit strings of length n, right? So, and there's 2 to the n bit strings of length n, which is capital N. Not sure why I chose the same letter, but forgive me. Okay. So for every uh, I can think of everything in L as being an index, a number between 1 and capital N. Okay. So that's why I say for every I in L, so for everything in a language, but treat as an index, we have a dictator function. Okay. It's going to take as input. Yeah. Okay. So there's some difference in scale going on. Okay. So L is n bit strings. Okay. So there's 2 to the n possibilities. Okay. And the function chi is defined over capital N bit strings. So there's 2 to the n possibilities, stuff like that. Okay. All right. So kind of D sub L denotes kind of the dictators corresponding to bit strings in the language. Okay. So there's something kind of weird going on with this change of scale. That's okay. Okay. So now a Boolean function, like one of those dictator functions, something that's a capital N bit string, can be encoded as a 2 to the n bit string. Okay, because there's only 2 options for the output, and otherwise there's 2 to the capital N inputs. So if you just think of like the truth table, where for every possible input you write down the output, that'll give you a 2 to the capital N bit string, and that's P. So our proof system, we are going to, for each X that's in the language, our quote-unquote proof is going to be the dictator function of X as a P-bit string. It's a little confusing because we've kind of changed scales a couple of times. Okay. This is one reason why it blows up so much. I mean, this is why it's blowing up so much. Okay. All right. Okay, so and then here's the test. So basically, yeah, I guess at some level, it's sort of saying that, no, let's go through it first. Okay, so what are we going to do? Given X, you want to know if X is in the language, okay? And you're also given a proof. You're basically going to try to test to see if Y is a dictator function for the index X. Okay? So that comes down to two tests. One, there's a way to test if Y is one of the dictators belonging to the language. Okay. And there's another test to test if Y is this dictator function in particular. Okay. And of course, if you concatenate that together, then you'll show that chi of X is in D sub L, which means X is in L. Okay. Seems kind of crazy. Right. Right. So this arguably doesn't look too complicated. And in fact, these two individual tests aren't necessarily too complicated either when we open them up later. Okay. But just taking a step back, so what is this sort of saying at a high level? Given at some level there's something definitely unusual about it because we sort of lifted it and we went from n to 2 to the n to 2 to the 2 to the n. So there's some change of scale that's a little bit confusing. Well, we sort of like basically lifted, took a step out, and then otherwise did something relatively simple. Granted, a lot of details are still hiding from you. But for me, I think one takeaway then is that if I'm not too worried about the length of the proof, so this one is not worried about the length of the proof. It blows it up, right? 2 to the 2 to the n. Then actually maybe it's not that hard to come up with a PCP style thing. Okay, so if you're willing to really blow up the length of the size of the proof, then it's not as hard to come up with a PCP type of algorithm where you only query a few bits. Okay, so I guess a big emphasis last time then, I mean, what that says about our discussion last class is that a lot of the effort was about trying to keep that graph CSP roughly the same size, making sure it's a constant degree expander before powering, make sure we get the alphabet down to a constant. A lot of the emphasis was on keeping things sparse as we added repetition and stuff to amplify unsat. That's one reason why we had to work so hard. Here, if we're not as worried about keeping the sizes small, then this sort of feels like a brute force lifting it up to some higher kind of dimensional thing and otherwise doing something relatively simple. Okay. Now, maybe here's one question that we can sort of ask. I'm not sure if this question will make sense at this stage, but let me point this out. Suppose I told you that each of these individually would take 3 queries. Okay. So suppose I told you there's some randomized way and you get some constant probability or something. Don't worry too much about the distance and the error rate exactly, but just at a high level, suppose I told you that there's a way to do each of these separately with say 3 bits. Querying 3 bits. Okay. But of course, you add that together, that will give you a 6-bit test. That much is okay. Now, the claim was that I only really need to test 3 bits overall. Okay. So, what I've kind of described here is, there's a 3-bit black box way to test if Y is in DL. Let's even pretend it's deterministic or something for simplicity. And there's a 3-bit way to test if y is equal to chi x. Okay, and that gives you a 6-bit thing where you do one after the other. Okay. Now, suppose you just want constant probability error. You're willing to give up a little bit more error than what those two things combined would give you. Okay, and that's fine. But you just want to get it down to 3 queries. And you can only do so in a relatively black box manner because that's all you have about these. How can I reduce the number of queries from 6 to 3 and possibly increasing my probability of failure? We can randomly pick one of the two. So if x is okay, so if x is bad and it's supposed to get rejected, one of these two should reject it. Okay. So if I pick one of them, I have a 1 in 2 chance of getting the one that rejects it, and then I'll successfully reject. So my error probability kind of goes up by a factor of 2, but it's still okay. And if it's going to accept, if it's going to pass both, then if I randomly choose one, it's going to pass that one. So you have these tricks, which is one reason why the query thing comes down really small, because also inside each of these, there's one of those tricks where roughly we go down from 6 to 3 or something. And that's one reason why the total number of queries can be kept so small, often at a cost of the constant factor in front of that error probability. There's some trade-off like that. So that's a common kind of trick in this area. Kind of ands, this test and that test and that test can be replaced with a choose one of them randomly and only actually do one test. Okay, that was fun. All right, so how does this relate to the PCP theorem, right? So I have something here that's sort of like universally testing a language or something, a very inefficient PCP. And I want to somehow turn that into, somehow I want to create some kind of device where I can take formulas in general and turn them into graph CSPs that roughly reflect the logic of the formula. Okay. All right, so this is what we'll do next. I don't know if this is guessable, but we'll see. Okay, so here then will be the actual black box, and there's a lot written, so I'll go through it slowly. All right, so let L be some language. So in our context, before we had a boolean function that we wanted to convert it to a graph. In this case, a language would be just all the bit strings that the boolean function would accept, would assign 1 to. And then everything else that's 0 is omitted from L. So L could be like the good strings. Okay. All right, so claim is that we can always create a graph CSP with 8 letters in the alphabet. Okay, so 0 through 7, although actually sometimes it's more convenient to think of that as bits of length 3. You'll see why. Okay. And in general, you'll have more vertices. We'll see how many. But of these, there will be n vertices in particular, such that if x is some n-bit string in the language, then there's some way to label all the vertices so that the ith vertex, ith distinguished vertex, gets the ith bit of x, and you satisfy everything. Okay, so there's some like n distinguished vertices, which sort of model like the n bits of x, so that if you do have values for x that will be accepted into the language, then you'll be able to label everything else and satisfy everything. The other is that if x is not in L, so if you have some n-bit string that's not in the language, okay, then for any labels on your vertices in your graph CSP, where those n distinguished vertices get assigned your n-bit string, um, your unstat will always be, I guess here y is barely okay. Um, your n-bit string will always be kind of proportional to the distance from the nearest point in the language. Okay. All right, this is very analogous to what was on the right. It's only presented in a slightly different language so that it's closer to what we just discussed. Okay. All right, so does anyone want to take a high-level guess how to do this? I don't know if it's guessable, but it might be fun just to explore to help you kind of chew on the ideas. So somehow, can we use this universal tester to sort of implement languages as graph CSPs? And I think it's impossible to actually guess it correctly, but I'm still curious to see if you guys have any wacky or fun ideas. Okay, we don't have any wacky or interesting ideas? That's fine. Okay, so we have our language L. Okay, so the theorem we want to prove is here. The universal tester thing is above it. Okay, so we have some universal tester for L. I'm calling that T. Okay, so what does T do? T takes as input, a bit string of length n, another bit string of length p, where p is much, much bigger than n. It also flips a finite number of coins. Okay, and so I'm letting omega denote the space of all possible outcomes of coins. So if it flips 10 coins, omega has size 2 to the 10. If it flips n coins, it has size 2 to the n. Okay. All right, so that much we know. How does T work? Well, okay. For any fixed outcome of coins, so some omega is like a fixed set of random bits for your tester, we know that T is going to query 3 bits of x or y and accept or reject x. Right? That's basically what we know. Okay. And our goal is to somehow simulate this in a graph, so to speak, in a testable way. Okay, so what are we going to do? All right, so here's the vertices. We are going to have n vertices that are going to kind of like be associated, or you're going to conceptualize them as the n bits of x. Okay, and we'll also have p vertices modeling the bits of y. And then we'll have one vertex for every possible outcome of coin tosses. Okay, so there's 3 types of vertices: the x vertices, the y vertices, and the coin toss vertices. Okay. And we're only going to allow x and y to, instead of having any letter between 0 and 7, it'll just be 0 or 1. Okay, if you want, you can make like a constraint that has a lot of weight or a lot of constraints or something, and stuff like that. Okay. You can make it like, you can make those vertices fail any constraint if it doesn't get assigned 0 or 1. So that you might as well give it 0 or 1. Okay. All right, so here are now the edges. So again, the goal is to sort of simulate what the tester does. Okay, so for every fixed outcome of coins, we're going to create 4 edges. And I'm just describing the 4 for one of these outcomes of coins. Okay, so what do we know? It's going to query 3 bits of x or y, and it's going to accept or reject x, right? So let's say, for example, and it could have been any combination of x's and y's, but just for concreteness, let's say it does the k1th bit of x, and then the k2th bit of x, and the k3th bit of y or something. The first one could have been from y or from x or whatever. I'm just choosing something kind of arbitrarily. Okay. Okay, so we're going to have 4 vertices involved. One is the vertex for that coin toss. And then we're going to have 1 vertex for each of the bits that gets probed. Okay. So VK1 was the vertex corresponding to the K1 index for X. VK2 was a K2's vertex of X. WK3 was a K3's vertex of Y, or K3's bit of Y. As usual, I'm just saying random words. Okay. All right. Okay. Okay. So we have these 4 edges. Okay. So okay. So these only get 0 or 1 label, 0, 1 label, 0, 1. So, well, yeah. What's one way to think of it? One way to think of it is, okay, I get a bit here, I get a bit here, I get a bit here, and I kind of send it to a central processing, and it does some logic, and it outputs something, right, at some high level. So we'll kind of try to encode that into constraints. So here is, oh man. Okay, so for what, just remember, we should think of each of these as being labeled 0 or 1. And whereas z omega will be labeled something from 0, 1 cubed. So z omega will get 3 bits in one of its labels, and the other 3 will effectively get 1 bit. And the way we'll enforce the 1 bit is to say, oh, if you actually gave it a number 2, 3, 4, 5, 6, or 7, it just automatically fails any constraint it participates in which case, yeah, why would you ever do that kind of thing? But it's simpler just to pretend that it gets assigned 0 or 1 for discussion. Okay, so z omega is going to sort of, the 3 bits for z omega from the label, you can think of them as 1 for each of those queries. Okay? Conceptually. So the first constraint is going to say, okay, the first bit of z omega should match the bit for vk1. Okay. The second bit, the second constraint for the second edge is going to be the corresponding thing for vk2. I keep screwing this up. Okay. It says that the second bit assigned to z omega should correspond to the bit that's assigned to vk2. And somewhere around here, where is it? Oh, okay. For the third one, the third bit of z should correspond to the corresponding third query bit. Okay. So okay. So those are the 3 constraints. Okay. And if it passes all 3 constraints, right? Now that means that the 3 bits of z omega do match the 3 bits from x and y. Okay. Now we're going to have one more edge that's really a self loop. So it's going to be some constraint that looks at z omega. Okay. So my question to you is, what is a reasonable, yeah, let's see if this is guessable. So okay, I want to now come up with a constraint for that self loop. Okay. At some level, I want that constraint to fail if t rejects x, or this choice of x, y, and this set of queries, right? So remember, what t would do for particular omega, it would query those 3 bits, look at those 3 bits, and then decide something, right? So what I kind of want to say is that if t is going to reject x, then at least one of these constraints that we're making fails. So far we've made 3 constraints, which is just making sure that the bits of z omega match the bits from the x and y. Okay. Now for z omega, I have, assuming they all accept, right? So let's look at a case where t would reject x for this proof y. and this particular omega. And I want to make sure that at least one of those constraints that we make fails. So in the bad case, all of these passes so far, in which case, okay, we have at z omega, the three letters correspond to those 3 bits of uh, x and y. Okay, so now your goal is to come up with a label for this self edge that'll make sure that, if those 3 bits are bad and would lead to t rejecting it, then so on and so forth. You're allowed to give like a long sentence description. It doesn't necessarily have a compact thing. It's not like a simple equation. It could be any logical description. So if t accepts, then I should pass this one, and if t rejects, I should reject it.
It's just the end of the straight constraint.
It's just a what?
The end function is a straight constraint.
Well, no, not quite. So, okay, so far, no, well, I guess not. Is it just the and? No, you kind of get the and for free. So what I would like to kind of get out of this whole thing is, if t would have accepted on omega, then I would like to satisfy all the constraints. If t would have rejected on omega, then I would like to fail at least one constraint. So you get like 25% error if it's rejecting altogether. So there's some relationship. Yeah.
Should it be something like the value at zw has to be equal to this thing that t accepts, or this other thing that t accepts, or and then all.
Yeah, exactly. So it's a little bit wordy, or it's not a short, compact thing. But remember, these constraints are just defined by, what are the letters you're going to accept? What are the labels you're going to accept? So we should just accept exactly what t would accept with the coin tosses omega. So if t gets coin toss omega, it makes 3 queries and looks at 3 bits. It looks at those 3 bits and either accepts or rejects, right? So we're going to let this constraint be satisfied by exactly the 3 bits that would have made t accept and not satisfied by the ones that rejected. Okay. So for this last constraint, I'm only going to take the bit strings that would have led t to accept for this particular set of coin tosses. Okay. All right, so actually not too clever or anything, but I think what's kind of going on is, so yeah, so what is, okay, so that's what you would do. You would do this for the whole graph, and then you can double check that we do satisfy the claim properties. But I think if you take a step back, what's kind of going on is, this T universal tester, because we didn't really we didn't open up that theorem, right? This is just looking at that theorem as a black box and turning it into a graph CSP. So what's great about this universal tester is that it's so simple. It only looks at 3 bits and flips some coins. That's really all we know about it, and it says yes or no. And it's sort of simple enough that you can sort of encode it in a graph with annotated with a little additional logic, right? Which is sort of what graph CSP is. Okay, so it only takes a few pairwise relationships to sort of encode the whole logic of a universal tester. Does that make any sense? I think one thing that's kind of quietly going on is all these things get bigger and bigger. For example, our graph size is like n plus 2 to the 2 to the p, or 2 to the 2 to the n, plus 2 to the number of coin tosses. So it's a bit bigger. It's a constant if n is a constant to begin with, but it is bigger. Okay. Okay, so that's how the universal tester leads to this graph CSP, which would have completed the last leg of that PCP theorem. Okay. All right. Okay. So now let's see how much of the tools we can build up towards that universal tester. Again, we're not really going to get to the end. Okay, but at least we can see some of the ideas that kind of go into it. so you can get some sense of what is needed. Okay, so I have to give a little bit of background on this field of analyzing Boolean functions. Okay, so you just want to focus on Boolean functions that take as input a bit string and output a real value. What's great about this is that it's closed under sums and rescaling, right? If I have two Boolean functions, I add them up, I have another Boolean function. If I have a Boolean function, I multiply it by 10, I have another Boolean function. Okay. You could think of them as vectors in 2 to the n dimensional space, which is sort of like the truth tables. So for every possible input, you write down the answer. Okay, so that will give you kind of 2 to the n slots, so a 2 to the n dimensional vector space. Now, it turns out when you analyze Boolean functions, at least notationally, instead of doing the standard inner product of just multiplying all the entries together, it's kind of convenient to normalize it. So this kind of inner product B, I guess B for Boolean, okay, is sort of the normal inner product, which in this case would be going over all the possible inputs, f of x times g of x, f of x times g of x, adding them up, but also taking their average over the total number of inputs. There's 2 to the n inputs. Okay. Since it's average, you can think of that as drawing a random input and multiplying the values together. Okay, so it turns out kind of makes some of the calculations a little cleaner to normalize and divide out that 2 to the n. It's not totally necessary. You would survive if you were working with the normal inner product, but it's cleaner. The corresponding norm would be the square root of this particular kind of inner product. All right, so okay, so from this, you get lots of like little clean rules. Like here's one. If you give me two functions f and g that map to 0, 1 in particular, okay, then the distance squared in this metric, which is this normalized Euclidean space, is exactly equal to the probability f of x is not equal to g of x. You guys see why? So if we just kind of plug into this, something like that, and it's a 1, 0 function. So if they're equal, then that will be 0 inside. If they're unequal, it'll be 1 inside. So it's okay. What are the odds they're unequal? By same calculations, if they're instead of functions from -1 and 1 instead of 0 and 1, all that's different now is that when they're unequal, the difference is 2. 2 squared is 4. Okay, so you get the same thing up to a factor of 4. Okay, how about this one? For any Boolean function mapping to -1, 1, the distance or the length of that function, so to speak, is 1. Is that one okay? Why? I'm sure you guys see this. Let's see who's going to be the one who's not too embarrassed to explain this. Yeah. So it's the expected value of f squared, and f squared is always 1. Okay. So you get these little cute identities. So if you start doing lots of exercise in this area, like big calculations disappear quickly because all this cute stuff sometimes comes into play. Okay. All right. So particularly important is this particular function chi s for various sets s subset of n. Or ignore the fun fact for the moment. Okay. So given some set S, some subset of indices, this function is going to look at X and it's going to take, how many, it's just going to sum up over those indices, okay, and do -1 to that sum. So it's basically computing the parity of the set S. How many ones, or is there an even or odd number of ones? Because if it's even, that thing's going to come out to 1, and if it's odd, it feels like it should come out to -1, but I wrote 0. Should be -1, right? Okay. Well, that's going to show up on many slides in the future, but hopefully it's not too confusing. Okay. All right. Okay, so sometimes it's also called a parity function over S because it's really just computing the parity over the indices. Okay. All right. So this also has lots of cute identities. For example, if you multiply chi S chi T, you get the chi of the symmetric difference between S and T. See why? So this kind of thing is going to be -1 to summing over the indices in I, in S I mean, plus the indices in T, xi, right? But indices that are in S and T are getting double counted. So they won't affect the parity overall. So the only ones that really matter are the ones that are in S or T, but not both. Okay. So they multiply together in a nice way. Here's another fun fact. If you take the expected value over all inputs, so you just randomly take an input, the expected value of any of these things is 0 unless it's the empty set, because that will always be equal to 1. Okay. Anyone see this? This one's trickier. At least, I suspect there's like a really cute way to do this, but for me, I just do it by induction, which is, oh, that's actually better. Okay, good. Oh, okay, but that's also okay. That's come by induction. Okay, but that's fine. So this thing is equal to, okay, you have to be a little bit nuanced in some ways, but what's the basic idea? Okay, no, let's do it this way. Let's do what you said. Okay. So we can fix the last bit to be 1 or the last bit to be -1. Uh, uh, okay, so it's going to differ slightly depending on whether the last bit is in S or not in S. So yeah, okay. Okay, so we can assume that the last bit is in S or something, and I just don't want to write it all out because it'll take forever. Okay, so uh, in that case, we'll have something like 1 expected value of chi S of X given xn is equal to 1 minus, nope, equal to 0 minus, because this is the -1 now, chi S of X given xn is equal to 1. Okay, this is assuming the nth bit is in S. And then by induction, each of those is 0. And in the 1-bit case, that's easy. All right. Good. So that's kind of cute. Okay. And then another thing is that if we take an inner product with respect to this normalized thingy, it's either equal to 1 if they're the same or 0 otherwise. Do you guys see this? I see all this like nodding immediately, but I don't believe you totally because it's a little too fast. Unless maybe you work in the area. Okay. I'll let you guys help me out. Okay, so I'll start here. What might I do next? Maybe we can at least plug in this definition, right? This should be of x, where x is a random input. Okay. Now what? You guys have the tools.
The case where they're the same is easier. Because they're the same that for every x, the two values will both be 1, or both be negative 1. Multiply will always be 1. So
Okay. Okay. But what about when they're different? Yeah. But they're multiplied, so we can't. Yeah. Staring right at you. Yeah. Okay. You can use that identity. And now, if they're different, if S and T are different, then S symmetric T is non-zero. So this is 0 if S is not equal to T. And if S is equal to T, then the symmetric difference is the empty set. And for the empty set, actually just a constant function of 1, because negative 1 to the 0 is 1, I think. Okay. If S is equal to T. Okay, so all this like cute stuff shows up when you do Boolean functions. Okay. All right. What do we call it when we have a bunch of vectors whose inner product is either 1 or 0? 1 if it's multiplied by itself and 0 otherwise. They're orthonormal. But you said orthonormal basis. Why is it a basis? They are orthonormal, right? Because if multiplied by each other, you get 1. Otherwise, you get 0. Why is it a basis? Right, so how big of a dimension vector space are we living in? N bits, 2 to the n. Yeah, so there's sort of, yeah, 2 to the n. And then how many possible chi-s's are there? How many choices of s? 2 to the n, one for every subset of n. Okay, so that actually gives you a maximum size independent set. It fleshes out, it fills out the dimension of the vector space. Okay, this is called the Fourier basis. Okay, and all right, so that's the Fourier basis. The so-called Fourier transform is just changing coordinates to this basis, right? Just like you can with any orthonormal basis. So I can always write f in terms of the basis chi-s by taking the inner product of f chi-s times chi-s. Okay. So I'm going to let f hat be that 2 to the n dimensional vector with coordinates indexed by subsets, but f hat sub s will be the inner product of f and that s parity function, the s's basis function. Okay, so that just changes. So you take f, which is originally just like the truth table encoding all the values, and you do a change of basis that sort of takes the inner product with a parity function. It's kind of bizarre. Okay, but that's all it is. I mean, in a matter of factly kind of way. Okay. Uh, One very nice property that we won't have time to verify is that the inner product in the original kind of Boolean inner product space, if you take it over to the Fourier analysis, you're going to get the same value except it was the standard inner product. So this is not normalized anymore. So really, I mean, because the scaling by 2 to the n is not a big deal. That's a constant scaling. So really, it's a distance preserving change of basis as well. So it's really a unitary transformation up to some fixed scaling that's sort of structurally unimportant. Okay. All right. Good. So let's try to do one of these tests today so you can see what one of these tests look like and what one of these analyses might be involved. Okay. This is actually used as the first step to a dictatorship, so it's not like I'm only doing this because it's a nice example. It also is the first step towards the eventual thing. All right, so linearity testing. So I have two functions. I have a function f. It's mapping to 0, 1. I'll say it's linear if f of x plus y is equal to f of x plus f of y mod 2. Okay, for all x and y. Okay. Now working in mod 2 is a little bit of annoying, at least kind of notationally. So it's a little bit more convenient to sort of switch to negative 1, 1 and work multiplicatively, and you don't have to write out mod 2 anymore. So it doesn't really feel like addition, but it still kind of is, and we'll still say it's linear. So now f is mapping to negative 1, 1 instead, and I'll say f of x plus y, f is linear, but f of x plus y is equal to f of x times f of y. Okay, so we should think of mapping 0 to 1 and 1 to negative 1, in which case kind of multiplying 1 and negative 1 with each other is exactly acting like adding 0 and 1 mod 2. Because negative 1 times negative 1 is like adding 1 plus 1. Because negative 1 times negative 1 gets you to 1, and 1 plus 1 gets you to 0. Okay, so it's the exact same algebraic structure, multiplying 1 and negative 1, or adding 0 and 1. Just we don't have to write mod 2 everywhere. And also, one thing nice is that in this other definition of linear, each of our basis functions is a linear function. All right, so we're going to test linearity in this kind of second multiplicative sense of the word, but it's not very hard to apply to the original sense because you can convert like the 0, 1 function to the negative 1, 1 function very easily by mapping 1 to, yeah. Okay. All right, so our goal is sort of to test if f is linear in some kind of approximate way. So if f is like really not linear, let's say like half the time for half of x's and y's it screws up or something, we should be able to figure that out. That's the kind of way we should think about it. Okay, so all right, so this is fun. You guys can actually try to guess this. So I'm giving you some function f, and I want to know if it's linear, okay, or really far from being linear. And you're working in a model where you have all the randomization in the world, but you don't know anything explicitly about the function. You don't know the inner workings, right? You can just query it. You can say, oh, what's f of this? What's f of that? Okay. How would you try to test linearity? If you don't know the answer already. I know some of you are in crypto and stuff. What's the silliest thing? Pick a negative and positive number? Well, you're taking as input bit strings. So I'm not even sure what a negative and positive number is here. Okay, we can take a random x and a random y. We can compute f of x plus y. We compute f of x and we compute f of y, or we can query f of x, query f of y, and query f of x plus y, and compare the values. Seems simple enough. I don't see what else you could even do in a black box world. Okay, so that is indeed the algorithm. We'll just sample x, y, and just double check to see if they agree. All right, so the algorithm itself is not too complicated. Then the analysis will take up the rest of our class. And hopefully not too much more than the rest of our class. Okay? All right, so here's the theorem statement. Well, yeah, here's the intermediate theorem statement. So the claim is that okay, what are the odds that you fail is greater than or equal to, in general, the minimum overall of these basis functions, the odds of a random input disagreeing was f. Okay, sort of a weird statement. Let me fast forward to an implication then, so that makes a little bit more sense. So, okay, or let me ask you guys this. Suppose this never failed, right? Suppose f always passed our test, which means I guess it's linear, right? But that means this is 0 on the right-hand side. Okay, so suppose f is linear, in which case this is 0. What does that say about this? Sorry? Every what? It has to be equal because now we're like sandwiched at 0 and 0. That means there's some s that agrees with f everywhere. So one takeaway is that every linear function is a parity function. Every linear function, f, that's mapping to -1, 1, and linear in this multiplicative sense of the word, is a parity function. So that's kind of cool. Okay. All right, let's prove this. I think we'll have time, as long as I don't think too much myself. Okay. Immediately a typo. Okay. All right, so for each notation, I'm going to let P just denote the probability on the right-hand side. Okay, the probability of failing the test. And Z is the indicator variable for failing the test. Okay, Z is 1 if you fail, 0 otherwise. Okay, so let's see this. Okay. All right, so the first claim is that Z is equal to 1 minus 1/4. Okay, so because we're working in a 1 or -1 space, if they're equal, then the difference is 0. F of x of f of y is times f of y is equal to f of x plus f of y. But if they're unequal, then the difference is 2, because one is 1 and the other one is -1. Okay, so we have this. Okay, so if they are, yeah, but it is right. Okay, so it seems like Z is actually an indicator variable that they are equal, right? I'm not wrong. Okay, so if the f of x f y is equal to f of x plus y, then you get 1 minus 0, so Z is equal to 1. Okay, so I think Z is supposed to indicate that you passed the test as opposed to fail, but we'll just see. Hopefully the rest of the notes hold up. Okay, so um, so okay, so if we expand this out, then you get some kind of like f squared x, f squared y, minus 2 fx fy plus f squared x plus y, right? Just expanding out that power, that squaring. Oh, okay, I see what you're saying. Like that, okay? But all those f squares are automatically 1. Okay, so we get like 1/2, plus 1/2 f of x, f of y, f of x plus y. Is that okay? All right. I'm going to write this like this, Just put 1 plus and 1/2 on the outside. That's the same thing. Okay. So I'm a little bit confused, but we'll have to find out. The expected value of z, okay, uh, okay, is equal to 1/2. I guess I should have just left the 1/2 there. 1/2 plus the expected value of x and y, f of x, f of y, f of x plus y, right? Okay. Okay, so let's look at this term. So I'm going to break this out into 2 stages. Like that, all right? And here's what we'll do. We're going to define this function h of x to be equal to the expected value over all random y. This is called a convolution. And people who do this kind of analysis use convolutions all the time, but here we're only going to use it once for the rest of your life, but that's okay. F of y, f of x plus y. Okay. In that case, this thing is equal to expected value over x of f of x, h of x, okay, which is f of h inner product, which is, we can do the change of basis like that, okay? All right, good. So, okay, so I feel like we're analyzing the probability that we do pass the test. Is that right? Okay, so I think I have some typos here, but we'll see. Okay. All right, so right now, P is actually the probability that we do pass the test. It's the expected value of Z. Okay. All right, so, all right, so now let's analyze okay, so the claim is that uh, in the Fourier basis, h of s squared, h of s is equal to f of s squared. Okay, we're running low, but hopefully we'll finish. Okay, so let's do this. Okay, let's see why. I just have some calculations written down and we'll see where it goes. So let's look at this. So this is h chi s p. Yeah. Okay, so if we expand out what h is again, we get the expected value over x and y of f of y, f of x plus y, standard basis function at s of x. Okay. And now, let me just check. Okay, so now by linearity, so because this function is linear, we have things like chi s of x plus y times chi s of y is equal to chi s of x, because we are working in bit strings. So x plus y, the two y's would just cancel each other out and go to 0, because everything's kind of mod 2. Okay. So by linearity, we get this. Okay. And interesting. Okay. So what's kind of cool now is that even conditional on y, so even if you fix y and then you add x is just randomly flipping all the bits. So x plus y is still effectively independent of y. So I can actually split these two terms like that. Okay. And then finally, uh, this is f chi s b. They both are f chi s b squared. So the randomization over y, that's obviously a random input, but also the random x plus y is still basically a random n-bit string. So you're taking the average product. Okay. So this is f hat s squared, and that is h hat s. All right, now we're very close to done. Okay. Again, I think we're analyzing probability that are equal, but that's okay. All right, so given this, we have p is equal to 1/2 plus 1/2, sort of like f hat squared, so to speak, right? 1/2 plus 1/2 summing over all subsets S, f hat S cubed. Okay. Somehow when we do this word analysis, like everything works out a little too cleanly. Okay. And this is at most 1/2 times, or plus 1/2, the maximum over all S, f hat S squared. Okay. Um, okay. Whew. Okay, so let's fix S to be the max. Okay. Then we're getting something like f hat S is at least 2p minus 1, where p is the probability that the test succeeds, we think, although my typo thought it was the odds that it fails. So we'll see if this works out. Okay. All right, so let's finish. 4 times the probability that they're not equal. Okay, this is going to be sort of odd. I'll have to figure out this bug at the end. Okay, which is equal to the distance in this Boolean metric squared, and that's equal to fb squared plus chi s squared minus 2 times their inner product. Okay. So this is 1, this is 1, and that's 2p minus 1. So I guess you get like 4. Oh, sorry. You get 2 minus 2 hat f of s. Okay. And we plug that in, and I guess we get 4p. Okay. Well, we get 4 minus 4p? Yes, I think you're right. Oh, okay, we get 4 times 1 minus p. Okay, good. Life is okay. Okay, so I'm glad everything worked out. My notes are completely messed up, and that's okay. I'll fix it later. It's a good way to test. We know what's going on. So P is the probability the test fails. 1 minus P is the probability the test. No, P is the probability the test succeeds. 1 minus P is the probability the test fails. So finally, we showed that the probability that, I don't know what I was writing there. It should be the probability that f of x is not equal to chi s of x. I didn't write of x. That most 4 times 1 minus P will cancel out the 4s. So finally, we get the probability that they're unequal is that most the probability the test fails. And that was the theorem statement, which ultimately also shows that all linear functions are parity functions. What is the moral takeaway? Since it's just a series of calculations we did once together, well, once you get a little bit of a flavor of the style of analysis in this, like there's a lot of change of basis, using these nice identities, there's a lot of like nice symmetry that comes up with this Fourier functions. The subsequent proofs would have been like this, but twice as long. And then, what is there to say? There's something very convenient about this change of basis that I'm having a little bit of trouble putting my finger on. But something kind of cute happened in the middle, right? Like the calculations we did were somewhat straightforward, modulo the slight confusion caused by my notes being wrong. Okay, but otherwise we didn't do anything nearly as complicated as taking the operator norm or stuff we were doing a couple of weeks ago. They're just like little cute algebraic identities you plug in and you roll through. So there's something very convenient about this change of basis that somehow makes it easier to analyze and work through these functions. Okay, and then also maybe the nature of the algorithm, the test being very simple, the analysis being a little bit longer, but ultimately the test is almost always simple, at least the ones I've written notes on. So maybe other things are more complicated, but okay. All right, so that's it. My only last question was, would you like to see the rest of this kind of stuff or just do something completely different in graphs or something else? Completely different? Okay, I see one head nod. That's good enough for me. All right. Okay, so we'll do something completely different next time, but at least if you wanted to understand the rest of the details of the PCP theorem, now you can. Okay, thanks.